Hi everyone, welcome back to the channel. It is a continuation of classes on coordination chemistry, and in this video we shall try to learn about the concept of coordination number and the way of determining the oxidation state of the central metal ion, and later we shall look over onto the nomenclature of the coordination compound, which is the most important factor we are supposed to learn in better understanding the structural details as well as the chemical properties of a coordination compound. So now we shall proceed into the topic directly. So firstly we shall go with the term coordination number. See, the heading itself will give you some hint regarding the core meaning of this particular topic, that is coordination number. That means if you consider a complex compound, as we said, there will be a central metal ion in the complex, and that central metal ion will be surrounded with certain definite number of ligands, and the ligand may be monodentate, bidentate, tridentate, tetradentate, hexadentate, whatever it may be. If you consider all the ligands which are surrounded by the central metal, which are surrounded the central metal ion, and if you count the total number of coordinate bonds formed by all the ligands present around the central metal ion, the total number of coordinate bonds formed by the surrounding ligands with the central metal ion is simply considered as coordination number. Or else we can say in some other way also, the total number of ligating atoms of the surrounding ligands that are directly linked to the central metal ion through coordinate bonds, that will be called as coordination number. That means, that's why I said in the very beginning, if you consider a ligand that may be a monodentate, bidentate or polydentate ligand. So in order to say about the coordination number of the central metal ion, we are supposed to count the number of ligating atoms present in each and every ligand which is surrounded around the central metal ion. So that is the simple way of saying about the term coordination number. So now we shall consider some simple examples to account for the how to determine the coordination number. So let us consider a simple one, say NiCO4 amps. This is one complex compound. So here the central metal ion is nickel and the ligand is carbon monoxide, and we know that carbon monoxide will be called as carbonyl, and we said carbon monoxide, that is carbonyl ligand, is a monodentate ligand. So monodentate means there will be only one ligating atom, and how many such ligating atoms are there? 4. Therefore there are 4 ligating atoms binding to the central metal ion, that is nickel, so that there will be 4 coordinate bonds are there, and that's why we can say the coordination number of this particular complex is equals to 4. And let us consider one more, FeCN 6 times with 4 minus negative charge. Means here we have taken a complex anion. Here we considered only the complex, the neutral complex, and here it is a complex anion. So here also the central metal ion is iron and the ligands are cyano, and there are 6 cyano ligands, and we know that cyano is once again a anionic monodentate ligand. So there will be only one ligating atom per ligand. So how many such? There are 6 monodentate cyano ligands, and that are binded to the central metal ion, that is iron. So there will be total of 6 coordinate bonds are there. Therefore the coordination number of this is 6. And one more, AgCl2 with 1 negative charge. So once again I have considered the complex anion, and here the central metal ion is Ag plus and the ligands are chloro, there are two chloro ligands, and chloro, these are the, once again, anionic monodentate ligand. So there are two ligands are there which are binded to silver, so the coordination number will be 2. And let us consider some typical examples like CO, NH3, Cl, and En twice with 2 positive charges. So in all these 3 exemplifications, we have only one type of ligand. That means they are homoleptic ligands. So homoleptic in the sense, if the central metal ion is bonded with only one type of ligands, then such complex compounds are called homoleptic ligands. They are called homoleptic ligands. Sorry, homoleptic complexes. Homoleptic complexes, that means in a complex, the central metal ion or central metal atom is bonded with only one type of ligands. And if you consider, the central metal ion is cobalt surrounded with or bonded with amine, chloro, as well as ethylene diamine. So more than one type of ligands are there, and they are bonded to central metal ion cobalt through coordinate bonds. So such complexes wherein the central metal ion is bonded to more than one type of ligands are called heteroleptic complexes. Heteroleptic complexes. So these are homoleptic, and this is one of the simple example for heteroleptic complex. Fine. So here we shall see the coordination number. So here we have totally 3 types of ligands: amine, chloro, and ethylene diamine. So we know that amine is a neutral monodentate ligand, chloro is a anionic monodentate ligand, En, that is ethylene diamine, which is a bidentate ligand. So bidentate in the sense there will be 2 ligating atoms, and how many such ligands are there? 2. So 2 2s are 4 plus 1 5 plus 1 6, and thus coordination number of this complex is 6. So shall go with one more example: PT, OX, and Cl, NH3 thrice. So this is not a complex ion, it is a neutral complex. And here we are supposed to look over into the coordination number. So here amine is a neutral monodentate ligand, chloro anionic monodentate ligand, OX, that is oxalato, it is a negative bidentate ligand, that is anionic bidentate ligand. So bidentate means here the number of ligating atoms are 2, and there is only one such bidentate ligand. So here we get 2 ligating atoms, plus 1 3 and plus 3, totally 6. So here the coordination number is once again 6. And we shall give one more, say Cr, H2O 4 times, Cl2 with 1 positive charge. So once again we are having complex cation. So here we got complex anions, and here we have complex cations. So here I am giving examples for all heteroleptic complexes. These are homoleptic and these are heteroleptic complexes. So here also there are H2O, aqua, so monodentate ligand, chloro, once again monodentate ligand. So 4 plus 2, totally 6. So here also coordination number is 6. So one last example let me give you. Say Cu, NH3 4 times with 2 positive charge. So copper is a central metal ion, Cu2 plus, and which is surrounded by 4 amine ligands, and amine is once again a neutral monodentate ligand, so one ligating atom, and there are 4 such ligands. Therefore, the coordination number of this particular complex is 4. So likewise, we can easily determine the coordination number of the central metal atom or ion, whatever it may be. It may be a homoleptic or a heteroleptic complex. Just we have to count how many ligating atoms are surrounded by the, how many ligating atoms are attached to the central metal atom or ion, just by counting the number of ligating atoms. Next is determination of oxidation state of central metal atom or ion. In order to give a proper name for a given coordination compound, it is very important to know the exact oxidation state of the central metal atom or ion present in a given complex. So, in order to find out the exact oxidation state of the central metal atom, we are supposed to know the density of the surrounded ligand as well as the nature of the ligand. That means whether the ligand is neutral, cationic or anionic. As well, we are supposed to well aware about the charge present on the ionic sphere of the complex salt. If complex ion is given, means it is very much easier to find out the oxidation state of central metal ion. Or else, if complex salt is given, then we are supposed to well aware the charge or the oxidation state present on the ionic sphere also. So now we shall consider a few of the examples for determining the oxidation state of the central metal atom. So first, let me consider CuNH3 4 times surrounded with the ionic sphere SO4, that is sulfate. So here CuNH3 4 times, it is the coordination sphere, and SO4 is ionic sphere. So when you given with a complex salt, in order to find out the oxidation state of the central metal atom or central metal ion, as I told, we should know the charge present on the ionic sphere. So we know that SO4 sulfate, which is having a charge of 2 minus. So in order to counterpart the 2 minus charge present on the ionic sphere, obviously the complex should have the opposite charge in equal magnitude. That means CuNH3 4 times, there will be 2 plus charge on it. So once you got off with a complex ion, that may be a complex anion or complex cation. So once you got off with complex ion, then it is very much easier to find out the oxidation state. So the oxidation state of the central metal ion will be taken as X plus the oxidation states of the constituting ligands, the algebraic sum of the oxidation states of all the constituting ligands should be equated to the charge present on the complex ion. So that way we can determine the oxidation state of the central metal ion. So the oxidation state of central metal ion, that is copper, is supposed to be determined, and here there are 4 amine ligands, and amine is a neutral monodentate ligand. So neutral in the sense the oxidation state or charge on the amine ligand will be 0 and there is no other ligand is present, and the algebraic sum of oxidation states of constituents of the coordination sphere should be equated to charge present on it. Then charge present is plus 2. So whole and solely it will become plus 2. That means in this complex, copper is existing in 2 plus oxidation state. So this is the way we can easily find out the oxidation state of the central metal ion. So let us consider one more. K4FeCN 6 times. So here the complex is FeCN6. This is the coordination sphere, and the ionic sphere is K4. There are 4 potassium ions, and we know that potassium is an alkali metal which will have an oxidation state of plus 1. So there are totally 4 positive charges. In order to counterpart these 4 positive charges, the complex is supposed to have the equal number of opposite charges with equal magnitude. So that the complex ion will come as FeCN6 4 minus. So once you got the complex ion, then the proceeding is very easy. So Fe, its oxidation state is supposed to be determined, plus there are 6 ligands, and nature of the ligand, cyanide is a monodentate ligand and it is an anionic ligand. So there will be 1 negative charge on this cyanide. So 6 into -1, and there is no other ligand is present, and this algebraic sum should be equated to charge on the complex, that is -4. So X is equals to 6 minus 4. So X is equals to +2, that is iron is present in 2+ oxidation state. So here it is ferro, since iron is in +2 state. And now we shall consider, so here I have taken homoleptic complexes. So now we shall look over into some heteroleptic complexes. So the first heteroleptic complex we can consider is CO NH3 twice Cl2 and En with 1+ charge. So here directly we have getting the complex ion. There is no ionic sphere at all, need not to worry, just we need the complex ion. And now, so we have 1, 2, 3 different types of ligands. So now we can proceed with the same procedure. The oxidation state of cobalt is supposed to be determined. So X, plus there are 2 amine ligands and it is a neutral. There are 2 chloroligands and each chloroligand will be having -1 charge, plus there is 1 ethylene diamine ligand and it's a neutral. So the algebraic sum is equals to charge of the complex. So whole and solely X -2 is equals to X -2 is equals to +1. So X is equals to +3. So here cobalt is present in 3+ oxidation state. So now we shall consider one more example, one peculiar case, NiCO 4 ions. So here you can notice there is no ionic sphere at all and there is no charge also on the complex. So not a big matter. The oxidation state of nickel is supposed to be determined. X, there are 4 carbonyl ligand and carbonyl is a neutral monodentate ligand. So 0, and there is no charge present on the complex. So that will be equals to 0. So thereby X is equals to 0. That means in this nickel is present in 0 oxidation state. So regarding this 0 oxidation state, we shall discuss in later videos. So firstly, this is the methodology we are supposed to follow in order to find out the oxidation state of the central metal ion, whatever it may be. It can be a homoleptic complex or it can be a heteroleptic complex. Also, the only thing we are supposed to remember is the nature as well as the denticity of the ligand. Now, we shall go into the main concept, that is nomenclature of coordination compounds. In order to give the proper names for the coordination compound, we have to follow certain rules, and based on each and every rule, how we are supposed to, or by following those rules, how we can give the names for a given complex compound, that we shall learn now. So the first rule is the cation is supposed to named first, then the anion. That means if you consider a complex salt, as we know, there will be 2 spheres in a complex salt. One is coordination sphere and other one is ionic sphere. The coordination sphere can exist as complex cation and complex anion. Similarly, the counterparting ionic sphere may exist in either in the form of cation or in the form of anion. So among the coordination and ionic sphere, the one which is in the form of cation, that's supposed to be named first, followed by the anion. So let us give the example for either of the type. See here, in case CuNH3 4 times SO4. So here the complex is, the coordination pair is written first, followed by the ionic pair. So we know the general IUPAC rule. While writing an ionic compound, first the cation will be written, followed by the anion. So here the coordination pair is the cation and the ionic pair is anion. So you should give the name for the coordination pair first, followed by the ionic pair. But if you come to the case of this one, K3FeCN 6 times. So here we got one more complex salt. Here the ionic pair is present first, followed by the coordination pair. That means here ionic pair is cation and coordination pair is anion. So here in this case, name of ionic pair should be given first, followed by the name of coordination pair. Okay, that is according to first rule. And now the second rule is, when you are giving the name for a coordination pair, in that coordination pair we know that there will be certain definite number of ligands and a central metal ion. Among central metal ion and ligands, the names of ligands are supposed to be named first when they are present in more number. When different ligands are present, the names of those ligands are supposed to be given in terms of alphabetical order. Once the names of all the ligands were given, then the name of central metal atom or ion is supposed to be given. Suppose when the identical ligands are present in multiple number, then rule number 3, we have to use the prefixes to indicate the number of identical ligands present. That is, if the same ligand is present in 2 number, the prefix di. If it is in 3, tri. If it is in 4 number, then it will be a prefix tetra. Like that, we have to use the prefixes in order to indicate the number of identical ligands present. Suppose we are having some complex ligands, so that creates an ambiguity in giving the names for those ligands if you use the common prefixes di, tri, tetra, penta, etc. If there occurs any ambiguity in using this normal prefixes for indicating the multiple number of the identical ligand, then instead of using the prefixes di, tri and tetra, we can go with other prefixes such as bis for 2, tris for 3 number, tetrakis for 4 numbers. Like that, we can use the other prefixes if there occurs an ambiguity. So these are the two other rules, the rule number 2 and rule number 3 we are supposed to follow. So let us consider one simple example. Say CO, Cl twice, NH3 4 times with one positive charge. So here I am considering the complex ion. So here we have more than one type of ligand, that is, we got an heteroleptic complex over here, and the ligands present are amine and chloro. So whatever the way we can write the position of the ligands while writing the formulae, but while giving the name, we are supposed to say the names of the ligands in alphabetical order, and we have to indicate the number of identical type of ligands present by using the prefixes. So here we have amine in 4 number, chloro in 2 number. So we should say the name like there are 4 number, so tetra, and the name of the ligand is amine. So as I have told you, we have to use the double M, tetra amine. So then the next ligand is chloro, which is in 2 number, and we said chloro. So Cl is a anionic ligand. The name of anionic ligand is supposed to end up with the letter O, that we have said in previous video. So you can cross check in my previous video regarding the names of the ligands. So there are 2 Cl ligands, so it is tetra amine. There are 2 number, so dichloro. So like this, we should give the names of the ligands. Thereafter, we have to go with the name of the central metal ion. Okay, so we can give one more example like fine, CO NH3 4 times and En. So here we will be having 3 plus, once again complex cation. So here again we are having two ligands. So one is amine, that is a monodentate ligand, and other one is En, that is ethylene diamine, which is a bidentate ligand. So which one should say first? So obviously the A alphabetical order should be followed. Amine, which is present in 4 number. So again tetra amine, ethylene diamine, ethylene diamine. So we have given in the alphabetical order. Then we have to give the name of the central metal atom. So in both the cases it will be cobalt. So here also it is cobalt. Suppose if you are having some complex ligands, so where we can use these prefixes, this is bis, tris and tetrakis. So now we shall see, so for example, let me go with chromium. So Cr, Cl and OX twice, and here also twice. Fine. So here also we got an heteroleptic complex, and sorry, okay, 3 minus. Fine. So here we got a complex anion. So here we have 2 chloro and 2 oxalato. It's a bidentate ligand. So 2 2s are 4 plus 2. Again the coordination number of chromium is 6 and the charge present on the chromium complex is 3 minus. So here chromium is in plus 3 oxidation state. So that's we shall see in the next rule. So here the name. So chloro starts with the alphabet C. Oxalato starts with the letter O. So first we should go with chloro. So there are 2 number. So dichloro, and there are 2 number. We cannot use dioxalato. Instead bisoxalato. So when we are having a complex ligands, we should go with the prefixes bis, tris and tetrakis. So this is according to rule number 2 and rule number 3, and here we have to see the name of the central metal ion, but here the case will get changed because in both these 2 cases we have a complex cation, but here we have the complex anion. So when you got a complex, if the coordination sphere is a complex anion, then the condition will get changed in giving the name of the central metal ion, that we shall see. 4th and 5th rule. So when the complex is an anion, then the name of the central metal ion is supposed to be end up with the suffix 8. So we should attach the suffix 8 to the name of the central metal ion. And at last, once we give the name of the ligands and the name of the central metal ion, depending on whether it is a complex cation or a neutral or complex anion, at last we are supposed to indicate the oxidation state of the central metal ion. That too, the oxidation number of that central metal ion is supposed to be indicated by a Roman numeral, and that's supposed to be indicated in a parenthesis, that is in small bracket at the end of the name of complex. So these 2 rules we shall apply at the end. So here we have given the name for all the ligands and the name of the central metal atom is written, central metal ion is written, and at last we are supposed to give the oxidation number. So here NH3 is a neutral ligand, need not to consider. So there are 2 negative ligands, so 2 minus, so X plus X minus 2 is equals to plus 1, so X is equals to plus 3. So here cobalt is in +3 oxidation state. So the oxidation state of cobalt should be indicated in Roman numeral at the end of the name of complex in the parenthesis. So the whole and sole name will be tetraamine dichloro cobalt 3. Since we have given the ion, should say as it is an ion. So if ionic sphere is given at the place of ion or instead of ion, we can write the name of the ionic sphere. And here, so tetraamine ethylene diamine, once again we should find out the oxidation state of the central metal ion, that is cobalt. So here both amine and ethylene diamine, both are neutral ligands only, so this won't give contribution in calculating the oxidation number of the cobalt. So that means when all the ligands are neutral, then oxidation state of the central metal ion will be equal to the charge present on the complex. So here NH3En, both are neutral ligands only, so the oxidation state of cobalt will be equals to charge present on the complex, that is 3+. So again cobalt 3, once again no ionic sphere is there, so we should mention it as ion. Then here it is a special case, so it is a complex anion. So first we should give the names of the ligand, so that we have given dichloro bis oxalato, and the central metal ion is chromium. But since the complex is an anion, so the name of the central metal ion is supposed to end up with the suffix -ate, and thus the central metal ion is chromium, so the name will be chrome 8. The name of the central metal ion will be written as chromate. And now we are supposed to find out the oxidation state. So here Cl, so it is -2, and OX is a bidentate ligand with 2 negative charges, so 2 2s are 4, so -4, and the total charge will be -3, and the oxidation state of chromium will be X. So -2 -4 will be -6. When it comes to the right hand side, it will become +6. 6 minus 3, it will be +3. So chromium is in +3 oxidation state. So dichloro bis oxalato chromate 3. Once again no ionic sphere is there, so it will be given as ion. So now we shall consider, we shall apply all these 5 rules, and now we shall see the name of a coordination complex provided with both coordination sphere and ionic sphere. So here we have few complex compounds, and we shall try to give names for these complex compounds. So here in this complex, first we have coordination sphere followed by the ionic sphere Cl. So here the coordination sphere is cation and Cl is anion. So first we should give the name for cation. In that in coordination sphere we should name the ligands first followed by the central metal ion, that is cobalt, and the ligands are NH3 and CO3. This is carbonato and this is amine. So first we should say the name of amines, and they are present in 4 number. So tetra amine, then carbonate is there, which is a bidentate ligand. So CO3, so carbonato, since that is only in 1 number. So tetraamine carbonato. So all the ligands were named. Then the name of the central metal ion. The central metal ion is cobalt. And now we should find out the oxidation state of it. So X plus carbonate is in 1 number, which is having 2 negative charges, and an amine is neutral ligand, need not to consider. The ionic sphere is Cl, which will be having -1, so it will be having +1. Okay, so that's equals to +1. So X minus 3 is equals to +1. So -3 when comes to the right hand side, so -2 when comes to the right hand side, it will become +2, +2 +1, so it will be +3. So cobalt is in +3 oxidation state. So cobalt 3, and now the ionic sphere present as anion, which is chloride. So that is the complete name of this complex compound, tetraamine carbonato cobalt 3 chloride. And now we shall come to this one. So here in this case, first we have the ionic sphere followed by, so Na3CO NO2 6 times. So here the ionic sphere is present is first, followed by the coordination sphere. So ionic sphere is cation, coordination sphere is anion. So first we should say the name of ionic sphere. See, when ligands are present in multiple number, we should indicate that in terms of, by using prefixes. But even though the ionic sphere is present in multiple number, no need to mention the number of components present in ionic sphere. Just by giving the name of that ionic sphere, we can proceed further to give the name of the corresponding coordination sphere. So here the ionic sphere is sodium. So though 3 sodium atoms are there, no need to mention the number, just it is enough to say sodium. So cation is finished. Now we have to go with anion. So complex anion. So first we should say the name of the ligand. So here we have NO2, that is nitrito, provided the ligating atom is N, which is an ambidentate ligand. So there are in 6 number. So for 6 the prefix will be hexa and the ligand name is nitrito. Ligand name is nitrito and the ligating atom is N. So sodium hexa nitrito N. Then we should say the name of the central metal ion, that is cobalt. Since the complex is complex anion, the name of the central metal ion should end up with the suffix ate. So it is cobaltate. And again we should find out the oxidation state. So there are 3 sodiums, so 3 positives, so there will be 3 negative charges. So NO2, it's an anionic ligand, so X, there will be 1 negative charge on each NO2, so plus 6 into minus 1, that's equals to minus 3. So minus 6 is equals to minus 3. So when it comes to the right hand side, plus 6 minus 3, so that will be plus 3. So cobalt is in plus 3 oxidation state. So cobaltate 3. That's about the name of this particular complex. And now third one. So AgNH3 twice Cl. So complex is cation. So first we should say the name of the ligand. So NH3 amine, which is present in 2 number. So it is diamine. And the central metal atom present is silver. And here it is 1 chloride with 1 minus charge. So here it will be plus 1. So silver is in plus 1 oxidation state. So diamine, silver, and the ionic sphere is chloride. And for this one, so again the coordination sphere itself is present in the form of cation, and it is a heteroleptic complex consisting of 1 monodentate and 1 bidentate ligand. So there are 2 chlorines and 2 ethylene diamine ligand. So it will be dichloro. Next, ethylene diamine, which is present in 2 number. It's a complex ligand. We should use the prefix bis, and the name of that complex ligand should be written in parenthesis. So bis ethylene diamine, close the bracket, and we should say the name of the central metal atom, that is chromium, and the oxidation state. So here SO4 charge is 2 minus, so it will be 2 plus. So what is the oxidation state? So X, so minus 2, it's a neutral ligand, need not to consider, that's equals to 2 plus, right? So minus 2, when comes to the right hand side, it will become plus 2. So whole and solely chromium. So minus 2 comes to the right hand side, it will become plus 2, plus 2, plus 2, it will be plus 4. So chromium is in plus 4 oxidation state. So chromium, the oxidation state should be written in Roman number followed by the ionic sphere, that is sulfate. And the last one here, the ionic sphere is potassium. So potassium. And the coordination sphere, the ligand is fluorine, which is present in 4 number. So tetra fluoro, and the central metal ion is boron, but this is anionic form, so the name should be end up with borate. So oxidation state, so here it is potassium with 1 plus, so it is 1 minus. So X minus 4 is equals to minus 1, so X is equals to plus 3. So borate 3. And that's the name of this particular complex. So in this way, I can give the names for any coordination complex depending upon whether the ligands are homodentate, or that is monodentate, bidentate or polydentate, whatever it may be. One important thing should be noticed is whether the ligand is complex or a simple one. If it is complex, we have to go with the prefixes bis, tris and tetrakis. Here is a special case of coordination compound. Here you can see we have 2 metal atoms, but there is no direct link between the metal atoms, but they have been joined through the ligands which are acting as bridges between these 2 ligands. Sometimes there will be only 1 bridging ligand, and sometimes like this there will be 2 bridging ligands. So how to give the names when the complex is having bridged ligands? So for this we can follow this rule. When you are having a ligand which is acting as a bridge between 2 metal atoms, then in order to say that a particular ligand is acting as a bridge between the 2 metal atoms, we have to use the Greek letter mu, and that is supposed to be written before the name of the ligand which is actually acting as a bridge. And here you can notice we have another ligand NH2. So we have already seen this ligand, that is NH3, which will be called as amine. So it is a neutral monodentate ligand. But here we have NH2. This will be having 2 negative charges, and this will be called as amido. Suppose you can notice here there are 3 hydrogens and we have removed 1 hydrogen and there is 2 negative charges. If you remove 1 more hydrogen, that will become NH, and again this will also carry 2 negative charges, and this will be called imido. So you can notice these 3 things: amine, amido and imido. So here we have the ligand NH2 which is having 2 negative charges, means it is a bidentate ligand, so it will be acting as a amido. It's supposed to be called as amido, which is acting as bidentate ligand. To say a bridging ligand. So how to give name for this one? So what to say now? So here first we should indicate the bridging ligands by mentioning the letter mu. So first we should write off both the bridging ligands. Then at a whole and soul we should say the total number of metal atoms and the total number of ligands present by indicating the names of the ligands first, followed by the name of the central metal ion, and all the remaining rules will be the same. So now we shall see here the bridging ligands are NH2 and NO2. Once again, there are 2 different bridging ligands. This is supposed to be indicated once again in alphabetical order. Amido starts with A, nitrito, and here the ligating atom is N. So here we are supposed to say amido first, followed by nitrito. So we should give the symbol mu first, mu, amido. Again, one more bridging ligand, mu, nitrito, and the ligating atom is N. Right. So then we have to go with the other ligands present. So other ligand present is amine. So 4 plus 4, totally 8 are there. So um, octaamine. Then there are 2 cobalt atoms, so it will be dicobalt, and the oxidation state of cobalt is 3 plus, so 3, and the ionic sphere is nitrate. So that is the name of this particular compound which is having the bridging ligand. So we shall consider one more example for the complex compound consisting of bridged ligands. So here is the compound NH3 5 times cobalt, and here between these 2 cobalt atoms this NH, that is imido, is acting as a bridge. So here in the above case we are having 2 bridging ligands, but here we have only one bridge, that is imido. So we shall give name for this. So first we should indicate the name of the bridging ligand by indicating the letter mu. So mu, and the bridged ligand is imido. Mu, imido. Then the remaining ligands has to be named with the alphabetical order. So we have 2 different kinds of ligands, NH3 and H2O. So NH3 amine, so AM. So H2O aqua, AQ. So first AM, that is amine should say. So here there are 5 amine ligands, and here there are 4. So 5 plus 4, 9. So nano amine, and there is one H2O aqua. So there are 2 cobalts, dicobalt, and cobalt is in 3 plus oxidation state, 3. So we have written the name of the coordination sphere which is acting as cation, and now we have to give the name for the ionic sphere, that is chloride. So in this way we can give names for the complex compounds consisting of normal ligands as well as bridged ligands. And that's about the nomenclature of mononuclear coordination compounds. And if you feel the video is worthy and useful, please like it, share it, and do subscribe to my channel and press the bell icon so that you will get the notification for any update in my channel. And in the next video we shall learn about Werner's theory and the calculation of effective atomic number of the coordination compound. Thank you.